All right, in this video, we're going to talk about the rate of change. Just to give you some heads up, we talked about how we can define the slope of the tangent line to a curve at a point by using the derivative concept. But that's not the only application. In fact, applications may occur for finding the rates of change in various fields. In fact, you can talk about the population growth rates and production rates, water flow rates, velocity and acceleration, and many more problems. For many more problems, you can talk about the rate of change of one variable with respect to another. When you hear the phrase rate of change, that means you're talking about the derivative of certain functions. And the example that I'm going to pick to describe this concept is going to be the motion of an object moving in a straight line. Again, there are many other applications. Essentially, we commonly use either a horizontal or a vertical line with a designated origin to represent the line of motion. So you can like go in this direction, upward or downward. And generally upward is always taken to be positive and downward is negative, or sometimes going to the right could be positive or going to the left being negative. Let's say that you have the function s providing you the position of an object as a function of time. So we call this function to be a position function. And the position, when we say position, let's say like here's the origin, and s is telling us where we are based on the origin. Are we here or here or here? So s is going to tell us exactly where the position of the object is in time. Then we can talk about a pre-calculus concept called the average velocity. Let's say like over a period of time, the object changes its position from s of t plus delta t minus s of t. So essentially, let's say like you're here at the time moment t plus delta t, and let's say like you were here at time t equals t. Okay, so the total distance that you travel from the time moment t and the time moment t plus delta t is going to be the difference between s of t plus delta t minus s of t plus delta t and s of t, so that the rate of change from t to t plus delta t is going to be the distance traveled divided by the elapsed time. So that's going to be called delta s over delta t. So delta s here is the difference of the positions from the time t equals t to t plus delta t. So this is again a pre-calculus concept, and we are not even talking about the derivative concept yet. So this is called the average velocity from this point to this point, because I travel from here to here. So my average velocity is found by this formula. And now I can talk about velocity, or in other words, instantaneous velocity of a moving object by letting delta t, which is the elapsed time, approaching zero. So this part is the average velocity, right? Average velocity. But just imagine like a very short period of time from one point to another, and if you want to find the average, if you want to find the instantaneous velocity over that a little time interval, you calculate the average velocity and let delta t go to zero, and that's going to be the instantaneous velocity. In fact, that is the derivative, because this definition is the definition of the derivative. So this is in fact the derivative of the displacement or position function. So if you know the position function, which in other words, you know exactly what the trajectory of the moving object is. By taking the time derivative of that, you can find the velocity of, or instantaneous velocity of the object. And velocity can be negative, zero, or positive. Negative means like you're going in an opposite direction based on the origin. So let's say like if the positive direction is this way, if your velocity is negative, that means you're going in this direction. Okay, but speed cannot be negative, so we generally take the absolute value of the velocity to find the speed of an object. We have a quick application of finding average velocity of a falling object. Let's say like we have a billiard ball dropped from a height of 100 feet. Okay, so the ball's height, s at time t, is given by the position function. You can easily see that at time, this is s of t, and at time t equals 0, when I substitute 0 for t, it's 100, so it tells me that originally the ball is at the height of 100 feet, but as the time evolves, you will see that the ball is going to drop, and s is going to provide you a lower value. And here S is measured in feet and T is measured in seconds. So the question is asking, like, find the average velocity of the ball over each of the following time intervals. So from time moment t equals 1 to t equals 2 seconds, or from t equals 1 to t equals 1.5 seconds, and maybe even a shorter period of time from t equals 1 to t equals 1.1. For finding the average velocity on the time interval 1 and 2, all I need to do is to check the distance traveled from t equals 1 to t equals 2. All I'm looking at the positions of the object, which are in fact s of 1 and s of 2. Plugging in 1 and 2 for t takes you all the way to 84 and 36. And by using the formula for the average velocity, so the total distance traveled is going to be 36 minus 84. And the total time traveled is 2 seconds minus 1 second. That's 1. So as you see that, average velocity is minus 48 because the ball is dropping, right, all the way down. So as I told you earlier, upward direction is always positive and downward is negative, right? Downward is negative. So that's why, I'll just correct this, okay? So that the velocity here, average velocity, is coming with the negative sign here. For the time interval 1 and 1/2, we're doing the same thing. We're looking at S of 1.5. S of 1 uh, was already calculated as 84. Okay, so that the average velocity is going to be the total distance traveled. So 64 minus 84 divided by the total time traveled. So it's 0.5 seconds, as you see. So if you do the division, you have the average velocity to be exactly equal to negative 40 feet per second. And let's just replicate the same method for the time interval 1 and 1.1. So essentially the average velocity is the total distance traveled, negative 3.36 divided by the time elapsed, which is 0.1 second. So that takes you all the way to negative 33.6 feet per second. So as you see that in this question, I'm trying to squeeze this interval all the way to 1 because I'm getting closer and closer to 1. So then you can talk about the instantaneous velocity at t equals 1. Instantaneous velocity at time t equals 1. And we know how to find that because we just discussed about it. The time derivative of this function, which we can find by using the rules that we just developed in the first two videos. In fact, negative 16 is a multiple. I'm going to use the power rule for differentiation. So putting 2 down and subtracting 1 from the power of t squared, so that makes it t. And you have a constant function here. The derivative of that is 0. So if you wrap it up, s prime, which is the function for velocity, is exactly equal to 32 times t. And if I want to find the instantaneous velocity at time t equals 1, all I'm going to look at here is s prime of 1, and that's equal to negative 32. And this is no surprise because on the interval 1 and 2, the average velocity was negative 48, and then it went down to negative 40, And then eventually on the short interval, 1.1, the velocity was negative 33.6. And if you just try squeezing this interval in the next step, let's say like you're talking about average velocity uh, for the interval 1 and 1.01, maybe 1 and 1.001. So that means you are approaching all the way to negative 32 for the instantaneous velocity. In this slide, I'm going to give you the formula for the position of any free falling object, neglecting the air resistance. And as you see, that S of t is a function of g, time, obviously, v sub 0 and s sub 0. And v sub 0 and s sub 0 are the initial velocity and position of the free falling object. And g is the acceleration due to gravity. And you have different units here. So if you're talking about US units, so you have g to be 32 feet per second squared, or if you use the metric system, it's 9.8 meters per second squared. And let's apply this definition to this example here using the derivative to find velocity, essentially. So let's say like we have a diver jumping from a platform that's already 32 feet above the water. As you see, this distance here is 32 feet. Okay. Well, the diver has the initial velocity of 16 feet per second. So the question is like, when does the diver hit the water, and what is the diver's velocity at the impact? Now let's use this formula here. We already have g, we already have the initial velocity and initial displacement of initial position of the diver. Let's try to make use of them. And here is the initial velocity. Since the diver jumps up, the velocity is positive, so that's why I use plus 16 here. And we also have 32 feet for the height of the platform, and that's also positive. So essentially, using the gravity due to the acceleration of the Earth, so we have a negative 16 t squared plus 16t plus 32. That describes the position of the diver in time. And the first question was asking like, when does the diver hit the water? Essentially when the S is exactly equal to 0. So when the position is 0, that means you hit the water. So for that reason, I'm going to set the position function to 0, and in this case, we're solving a quadratic. You can in fact either use the quadratic formula, or you can try to factor this polynomial. In fact, this polynomial is factored as like negative 16, t plus 1, and t minus 2. That takes you to t equals minus 1 or 2. Well, obviously t refers to time. Time cannot be negative, so this is sort of like not, this is redundant. So we're going to take t equals 2. So after the diver jumps up, after 2 seconds, the diver is going to hit the water. And the second part of the question is asking like, what is the diver's velocity at impact? So all we need is the velocity as a function. And we're given s of t, so we're going to take the derivative of this function by using, obviously, all the rules that we learned in this section, in fact, in the first 2 videos, constant multiple rule, power rule, and everything. So it turns out that s prime of t is negative 32 t plus 16, and the time of the impact is 2 seconds. So if you plug in 2 for t, then we see that at the impact, the diver's velocity is negative 48 feet per second. All right, that answers 2 questions being asked here. There are alternate versions of this problem, and the question have may also ask like, when is the diver's velocity 0? Obviously right at this point here, right? The diver's velocity is going to be 0 because that's going to be an instantaneous moment where the velocity is just going to be 0. So you can also answer those questions. And I think this ends everything with this question. In fact, We're completely done with the learning objectives of this section, because we have just talked about the rates of change business, and there are various real world applications of rates of change, and you're going to see a few of them in the homework assignment. So I'm going to close this video. Thanks for watching. I'll see you in another video. Bye.